네, 안녕하세요. 오늘 수업을 이제 진행을 하도록 하겠습니다. 우리가 이제 저번 시간까지 그 컴퓨터 프로세서에 이제 쓰이는 그 arithmetic unit을 구현하기 위한 그런 arithmetic number system의 기본에 대해서 그 스페시피케이션에 대해서 우리가 이제 배웠죠. 뭐 컴퓨터라는 그런 컴퓨터 프로세서가 그 바이너리 포맷, 바이너리 넘버 이런 이렇게 이진수 우리 그 한국어로 하면 그 바이너리 넘버들을 이제 다루기 때문에 그 넘버 시스템을 어떻게 이제 구현하느냐 뭐 이런 이슈들을 이제 배웠고요. 그리고 이제 중요한 거는 이제 컴퓨터 프로세서에서 이제 가장 중요한 오퍼레이션이라고 하면은 다른 오퍼레이션도 물론 중요해요. 근데 가장 중요한 오퍼레이션이라고 하면은 이제 arithmetic operations가 될 텐데 그 arithmetic operations를 어떻게 이제 구현할 것이냐. 뭐 예를 들어서 이제 우리가 이제 arithmetic operation이 뭐가 있었죠? add, 그 다음에 subtract, multiply, and divide. 이게 이제 가장 기본적인 그런 arithmetic operation이었죠. 그런 부분들을 이제 컴퓨터 하드웨어로 어떻게 이제 만들 수 있느냐 이런 부분에 대해서 우리가 이제 이야기를 나눴습니다. 사실 뭐 저번 챕터 3는 모양이 적기도 하고 그리고 이제 사실은 이제 디지털 로직 디자인에서 이제 보통은 커버를 하는 그런 내용이기 때문에 제가 이제 조금 빠르게 이제 넘어갔습니다. 그런데 오타가 있었죠. 이게 아니네. Let me see. 오케이. 한 학생이 이제 뭐 얘기를 해줬는데 여기가 우리가 이제 플로팅 포인트가 이제 싱글 프리시전이 있고 이제 더블 프리시전이 있다라고 했죠. 어쨌든 이제 저번 시간에 이제 제가 다뤘던 내용 중에 이제 가장 핵심이 되는 내용이 이제 플로팅 포인트에 대한 그런 내용인데 그 싱글 프리시전하고 이제 더블 프리시전을 우리가 표현하는 방법이 이제 조금 달랐습니다. 어쨌든 이제 기본적으로는 이렇게 사인 비트하고 그 다음에 엑스포넌트, 그 다음에 프랙션 파트로 이제 나누어지고요. 그 다음에 각각의 요 필드들이 이제 의미하는 바가 요 밑에 있는 식과 같이 된다라고 했었죠. 그래서 사인은 뭐죠? 사인 빛을 나타내고요. 마이너스는 1, 그 다음에 플러스는 0라고 했고 프랙션은 1 플러스 프랙션입니다. 그러니까 1 포인트 블라블라블라블라 이렇게 이런 식으로 나타날 때 요 소수점 아래 파트가 이제 프랙션이 된다라고 했었죠. 그 다음에 엑스포넌트는 뭐 이렇게 표시가 되는, 그러니까는 표현이 되는데 중요한 것이 이 바이어스가 중요하다라고 했습니다. 뭐 엑스포넌트는 보통 우리가 이제 바이너리 넘버를 투스 컴플리먼트 넘버로 표현을 하는데 엑스포넌트 같은 경우는 그렇게 표현하지 않아요. 이런 식으로 표현을 하고 있고요. 그러니까는 약간 뭐 기본적으로는 unsigned지만은 뭐 unsigned라고 말하기도 좀 애매한 그런 표현 방식을 쓰고 있다는 거죠. 이 바이어스가 싱글 프리시전이냐, 그 다음에 더블 프리시전이냐, 요거에 따라서 이제 달라진다라고 했습니다. 근데 여기 오타가 있었죠. 지금 이제 제가 고쳤는데 이게 처음에는 이제 1203, 그러니까는 1203으로 돼 있었는데 이게 아니에요. 1023입니다. 더블 프리시전이니까는 싱글 프리시전일 때는 바이어스 밸류가 127, 그 다음에 더블 프리시전일 때는 바이어스가 1023가 됩니다. So there was a typo in this slide. So actually in the exponent part of the floating point number can be expressed as the exponent minus bias value, and then this bias value is different for the different type precision of the floating point number. So there are two types of precision of the floating point number, the single precision and the double precision number. This is because with the different type of the precision, so we can change the resolution of the floating point number. Also, we can change the size of the floating point number. So for the single precision floating point number, the bias value is the 127, and then for the double precision floating point number, the bias is the 1023. But there was a typo here. So actually in the previous slide, so this value was the 1203, but actually this bias value for the double precision floating point number is the 1023. So I fixed this error, and then sorry for the typo. 예, 그래서 요거가 이제 1023라는 거를 여러분들이 잘 이제 기억을 해주시면 되겠습니다. 그다음에 뭐 레인지라든지 뭐 이런 부분들 다 설명을 했고요. 그다음에 뭐 프레시전을 굉장히 이제 사이즈가 큰데 어디까지 이제 표현이 될 거냐? 뭐 실제로는 우리가 이제 그 10진수로 데시멀 넘버로 이제 표현할 경우에는 싱글 프레시전 같은 경우에는 뭐 소수점 밑에 6자리, 더블 프레시전 같은 경우는 소수점 밑에 16자리까지 표현을 할 수가 있다. 이제 그거를 이제 보여준 겁니다. 뭐 어쨌든 뭐랄까, 그러니까 넘버 시스템은 어쩔 수 없죠. 우리의 그 모든 자연 현상을 그냥 픽스드 포인트 넘버, 픽스드 사이즈를 가지고 있는 넘버 시스템으로 이제 표현하는 거는 이제 불가능합니다. 결국 우리는 넘버 시스템을 이제 쓰려면은 넘버 시스템이 표현할 수 있는 레졸루션이 어디까지냐를 좀 이제 고려를 해가지고 이제 써야 되는 거죠. 일상생 우리 in real world에서도 그 in reality 우리도 이제 넘버 시스템의 그 레졸루션을 제한을 해서 쓰고 있죠. 뭐 예를 들어서 내가 숙제를 할 때는 홈워크 할 때는 소수점 밑에 2자리까지 계산을 해라. 뭐 이런 유효 숫자를 이제 제시를 하는 거죠. 왜냐면은 이제 표현할 수가 없으니까. That's the same for the computer processor, computer hardware, and computer number system. 이죠? 네. 그리고 숙제 얘기를 했어요. 예, 숙제가 올라왔습니다. 블랙보드에. 그러니까는, 그리고 이번 숙제는 사실 저번 숙제는 이제 챕터 1을 커버를 했고요. 이번 숙제는 챕터 2 and 3를 커버를 했는데, 문제 수도 많고, 뭐, 문제 수준도 조금은 어렵다고 생각을 하고 있습니다. 그러니까 이제 빨리 이제 시작을 해서, 해줬으면 좋겠고요. 그리고 이제 빨리 시작한 훌륭한 학생들이, 그 문제 8번에 이제 오류를 발견해서, 오류를 제가 이제 수정을 해서 다시 올렸습니다. 그러니까는, 그 수정된 문제를 받아서, 해주시기 바랍니다. 플로팅 포인트 넘버를 했고, 그 다음에 디노멀 넘버라는 것이 있다라고 했습니다. 이거는 아주 작은 숫자, 크기가 아주 작은 숫자죠. 그러니까는 거의 0에 가까운 숫자를 나타내는 방법을 따로 정의를 했고, 그 다음에 약간 이제 특수한 뭐 인피니티라든지 아니면은 not a number 이런 거 아마 여러분들 많이 볼 수 있을 겁니다. C나 뭐 엑셀로 작성을 하다 보면은 뭐 divide by zero라든지 아니면 뭐 넘버로 표현할 수 없다라든지 이런 그 데이터들은 NaN이라고 이제 써 있는 경우를 여러분들이 볼 수 있을 것입니다. 그리고 예. 그다음에 이제 플로팅 포인트 넘버에서 여러분들이 조금 임플리멘테이션 이슈로 생각을 해야 될 것은 어쨌든 플로팅 포인트 넘버의 arithmetic은 이렇게 여러 단계를 거쳐야 돼요. 우리가 보통 이제 뭐 인티저나 이제 인티저 타입은 뭐 adder나 subtractor 같은 경우는 굉장히 심플한 하드웨어로 구현이 가능하지만 플로팅 포인트 넘버는 이렇게 여러 단계를 거쳐면서 계산을 해야 된다. 근데 이거는 in real world도 마찬가지라고 했죠. 우리가 이제 뭐 10진수 같은 경우에는 뭐 쉽게 뭐 익숙하니까는 뭐 빠르게 계산을 하지만 그렇지만은 실제적으로는 10진수도 이렇게 여러 스텝을 거쳐서 우리가 계산을 합니다. 플로팅 포인트도 마찬가지예요. 컴퓨터의 뭐 넘버 시스템은 뭐 별로 다를 게 없어요. 우리가 쓰는 거랑. 그래서 이제 플로팅 포인트 넘버는 adder든 subtractor든 multiplier든 디바이더든 거의 비슷한 컴플렉시티와 거의 비슷한 그 딜레이, 엑스큐션 타임을 가지고 있습니다. 그 부분을 고려하고 해야 되고요. 또 엑스큐션 타임은 보통은 인티저보다 이제 길다라고 여러분들이 생각을 하는 것이 좋습니다. 그렇기 때문에 이제 뭐 컴퓨터의 역사를 보더라도 처음에 인티저 유닛이 먼저 나왔고 플로팅 포인트 유닛은 코 프로세서, 그러니까 다른 칩으로 구현을 했고요. 그 지금에서야 이제 아주 그것도 옛날이긴 하지만 어쨌든 인티저가 먼저 나오고 그 다음에 플로팅 포인트 유닛이 나중에 들어가는 형태로 이렇게 컴퓨터 프로세서가 발전을 해왔습니다. 네, 이렇게 했고 그 다음에 플로팅 포인트 넘버랑 그 다음에 인티저 타임 넘버는 서로 다른 레지스터 파일을 쓴다. 세퍼레이트를 해줘요. 여러 가지 이제 뭐 임플리멘테이션적인 이슈도 있겠지만은 어쨌든 플로팅 포인트 넘버가 딜레이도 길고 엑스큐션 타임이 이제 길기 때문에 그 컨트롤을 조금은 더 단순화하기 위해서 플로팅 포인트 레지스터 파일이랑 그 다음에 인티저 타입 레지스터 파일은 보통 이제 구분을 해줍니다. 뭐 리스크 5 같은 경우에는 뭐 어떤 버전에 따라서 어떤 거는 인티저 타입만 지원하고 어떤 거는 플로팅 포인트까지 지원하고 뭐 이렇게 또 나누어지기 때문에 뭐 인스트럭션 셋 아키텍처에서도 그 레지스터는 분리를 해놓고 있어요. 뭐 서브로드 패러리즘 이렇게 뭐 해서 챕터 3를 이제 끝냈습니다. So if you have any question and post your questions on the blackboard or piazza, please. 네. 그래서 뭐 리뷰를 이제 간단하게 이제 진행을 했습니다. 네. 네. 그래서 이제 오늘부터는 이제 챕터 4를 이제 다루도록 하겠습니다. 챕터 4는 뭐 그냥 basically 그 컴퓨터 프로세서의 implementation 이슈에 대해서 뭐 자세하게 이제 다루고 있습니다. 그래서 여러분들이 사실은 이제 컴퓨터 수업을 들었다, 컴퓨터 구조 수업을 들었다 하면은 뭐 챕터 4의 내용과 챕터 5 내용이 사실은 제가 생각하기에는 뭐 중요하다라고 이제 생각합니다. 가장 중요한 것들 중에 하나입니다. 그렇다고 뭐 다른 게 안 중요하다는 건 아니고요. 근데 여러분들이 최소한 이제 컴퓨터 구조 수업을 들었다. 뭐 예를 들어서 어떤 수업을 들었을 때 우리가 항상 뭐 이 수업을 들었으면은 뭐는 기억해야 된다 이런 게 있잖아요. 뭐 예를 들어서 이제 우리가 이제 뭐예요? 시노미 시스템, 시그널 앤 시스템즈를 들으면은 푸리에 트랜스폼은 기억을 해야죠. 그거와 마찬가지로 여기 컴퓨터 아키텍처 과목을 여러분들이 들었다라고 하면은 최소한 이 챕터 4의 내용, 파이프라인 하고 메모리 시스템은 여러분들이 기억을 해야 됩니다. So from now on, I will cover the chapter 4 of the textbook. What is the content? The content of the chapter 4 is how to implement the computer processor in hardware. So actually, in the chapter 4, I will cover the actual architecture of the computer processor. So this architecture covers the process architecture. And then in the chapter 4, we will cover some more detailed architecture of the computer processor, including some single cycle processor and the pipeline processor architecture. So, in my opinion, in the computer architecture, undergraduate computer architecture course, the content of the chapter 4 and chapter 5 is one of the most important contents in this course. So, if you take this course, then you need to remember the concept of pipelining first, and then also another concept of some important concept is the memory hierarchy and memory system of the computer system. So this is a very important part of this course. So focus on studying and keep keep working hard in this course. So this is the introduction of this chapter, and then this slide also include what we learned until this chapter. So in the chapter 1, we learned about some performance of the computer system and performance metric of the computer hardware. So what's the important thing of the computer performance is the execution time. So you need to remember that execution time execution time is the inverse of the computer performance. Yeah. And then what component determines this execution time of the computer system? So that means that what component and then which component determines the execution time of some application which runs on the computer hardware. So we learned that execution time of the computer system is determined by number of instruction multiplied by CPI, clock per instruction, multiplied by clock period. So this is the inverse of the clock frequency. So you need to remember that this metric for the computer performance and the software performance. So this is the performance of the computer system, the computer processor. And then as a computer engineer, researcher, actually, if you work on some computer architecture field or some computer hardware related field, so you need to focus on the performance and cost of the computer system. So the first factor of the better computer system is the performance, and then the second is the power, and then power consumption or some cost issues. So this performance of the computer system is determined by the actually there are many factors to determine the performance of the computer system. So we know that the instruction count is also important. So which factor determines the instruction count? The algorithm, then your programs. But this is the software part, and then this software part. So as a computer architect engineer, as a computer architect, and then if you focus on the computer hardware system, then we cannot change the impact of this instruction count. This is the part of the software engineering, also compiler and operating system. And then instruction set architecture. So this is the this part. Where is the pointer? Okay. So this is the instruction. This instruction count part is determined by the software area, software engineering. So then this instruction count is determined by the instruction set architecture and compiler. And compiler is also very important. But if we design the computer hardware, then which part is important? So computer hardware determines the performance of actually the metric of CPI and clock rate, clock period. So this CPI and cycle time, clock cycle time is the clock period determined by CPU hardware. And in this chapter, so we will cover how to implement CPU hardware. That means how to design the architecture of the computer processor. So actually, this is so we will cover the instruction set architecture in chapter 2, and then we will cover the how to implement and how to design computer hardware architecture, CPU architecture in chapter 4. And this so as I mentioned, the content covered by this chapter 4 is very important, And then you need to remember the concept of pipelining, and then some performance degradation factors such as hazard is very important. So in this chapter, we will implement some pipeline processor architecture of the RISC-V processor. So that means that we will design the processor architecture that support in RISC-V instruction set architecture. So that means so hardware that support RISC-V instruction set architecture. So what does that mean? So in chapter 2, we learned about the RISC-V instruction set architecture, and then we learned that what is instruction set architecture? Instruction set architecture is the interface between computer software and computer hardware. So that means that instruction set architecture is the promise or protocol or contraction between the software and hardware. That means that instruction set architecture defines the operation of the instruction. So what is the operation of the instruction? So this is similar to the function. So here is the input. So some inputs are input data is called the operands, and then so some operands are input to the computer hardware, and computer processor is the hardware, or some computer processor or CPU. Then some promised output, the result of the instruction is generated, and this result is defined by the instruction set architecture. Also, the other parts, some other other parts are also defined by the instruction set architecture. What are they? Such as some number of register files, and then some format of the instructions, and then some status registers, and then also all of the details are defined by this instruction set architecture. Then the hardware need to support the operation of this instruction set architecture. And then what is not defined by the instruction set architecture? The execution time or some delay of the instruction, each instruction. So that means that in instruction set architecture, this execution time is not defined. For example, so that means that, so this is some example of the instructions add x1, x2, x3. So actually the instruction set architecture defines the result of this add instruction, so operation of this add instruction, but ISA does not define when the result will be generated by this instruction. So that means that when the add instruction is executed in the computer hardware or computer CPU, then this result can be generated after 10 nanoseconds, or after 100 nanoseconds, or after 1 millisecond. All cases are possible. So the part depends on the architecture or implementation of the computer hardware, but the customers want some better computer system, or better CPU, or better computer processors. So the duty it's not a duty. So some it may be the duty. Yeah, duty of the computer architect or computer hardware engineer is to design or implement the efficient and fast processor. So that means that if we reduce the execution time of this add instruction as the 1 nanosecond, 10 nanosecond, 100 nanosecond, but customers will like the best processor. That means if this add instruction complete in 1 nanosecond, then customers will choose this processor, the best processor. Sorry. So in this chapter, we will learn how to implement and how to design the architecture of the computer processor. But if these processors support some all kinds of RISC-V instructions, then this chapter will be very complicated, very complex, and hard to understand. So in this chapter, we will support the very simplified version of the RISC-V instruction set architecture. So this is the simplified version, but we will cover the realistic pipeline version. So what does realistic pipeline version mean? So that means that it's the very actually in the real implementation of the computer hardware, we applied some 5-stage pipelines, and then this real implementation or real hardware architecture is also covered by this chapter or this textbook. So it's the realistic pipeline version. So it really works. So for the simplified version, this hardware will support the limited set of instructions, RISC-V instructions. So we will cover this hardware will support the only 2 types of memory instructions, like load double word, LD, and then store double word, SD, and then arithmetic logical instructions, add, sub, and or instructions, then control instructions like BEQ, branch, if, equal. So the hardware and then the computer processor covered by this chapter will support only these instructions, a very simplified version. Okay, let's review how the instructions are executed in the computer hardware. So the role of the computer hardware engineer or computer architect to design the computer hardware that supports the operation of the instructions. So in order to implement these instructions as computer hardware, we need to understand the operation of the instruction first. So let's see the operation of the instruction. So first, the instructions are, actually we learned in the chapter 2, instructions are stored in the memory and then as the data. And then each instruction is indexed by address of the instruction, address of this memory. So, and it's obvious. So if we want to access the data stored in the memory, so we need to know the address of this data, the target data. And then, so we need to know the address of the instruction. And then this address of the instruction is called, this is very important, PC, program counter. So when the computer instruction is executed in the computer processor, then the first is the data stored in the memory should be fetched or moved to the computer processor, indexed by and pointed by address of the instruction, and then this address is called program counter. So the first we need to define the PC. That means that the computer hardware or computer processor first define the program counter of the instruction in order to execute to fetch this instruction from the memory. So first we need to define the PC, the program counter, and then with this PC, we computer processor access the instruction memory and then fetch instruction from the memory. So it's called instruction memory. So actually, in the chapter 2, we learned that the instructions are stored in the main memory, so DRAM. But in this slide, I mentioned the instruction memory. So it's a different memory, maybe, but we will learn some different hierarchy of the memory system in the chapter 5. But in this chapter, we assume that the instructions are stored in the instruction memory, which exists inside of the computer processor. So actually, DRAM or main memory is located outside of the computer processor, but these instructions are fetched to the instruction memory IM that exists inside of the processor. So actually, in the computer in the chapter, we assume that the instructions are stored in the instruction memory. So as sorry. as I as I explained, we assume that the instructions are stored in the instruction memory, and then in order to access or in order to read the date instructions from the instruction memory, so we need to define the program counter value. And then, so let's see some other example like add x1, x2, and x3. This is an example of arithmetic instructions of risk 5. And then if you see this instruction, let's review that chapter 2, then what is required? What are required? So this instruction requires two operands, and then the data should be read from the register file. So the data should be read. Data is read from the register file. Also, this instruction store the result to the destination register. So that means that this instruction need to read two operands from the register file. The register file is the kind of memory, so it's very similar to some special memory. And then also this instruction need to write the result data to the register file. So that means that this computer hardware needs register file. And then the register file is accessed by the register numbers. So register file, and then with register, this operation is also required. So that means the computer hardware. So we need to implement this operation of the arithmetic instruction. It's very also, this arithmetic instruction need to perform the add operation. So that means that we need the hardware adder. We learned in the chapter 3. So, and then also there are other types of instructions like a subtract or AND, logical AND or logical OR, and some different types of instructions. So these all kinds of arithmetic or logical instructions should be performed in the computer hardware. And then in order to support this operation, the computer hardware equip ALU. So ALU is ALU means arithmetic logic unit. So that means that all arithmetic or logic operations are performed by this ALU, execution unit. So this execution unit calculates the arithmetic result and then the memory address of the load and store. So actually for the web load and store instructions, we need to generate the memory address with some base address plus offset, the immediate value. So that means that this load and store instruction also need add operation. So arithmetic is some add, subtract, multiply, divider, and some logical instruction like AND, OR, exclusive, or some other different type of instructions. Also, the branch comparison. So in order to support the branch operation, like a BQ, X1 and X2, and then target. So what is required? So we need to compare the values stored in the two different register files, X1 and X2. And then for comparison, we need to perform subtraction operation. So these all type of arithmetic operation and logical operation is performed by the ALU, arithmetic logical unit. So computer hardware requires the arithmetic and logical unit. Also, when the load and store instructions are executed, then this instruction need to access memory because the all data is stored in the memory. And then in this chapter, actually, we will learn about the memory hierarchy in the next chapter, in chapter 5. But in this chapter, we assume that the data is stored in the data memory, which exists also inside of computer processor. So this load and store need to access the data memory, the separated data memory. And then in order to execute, in order to fetch the next instruction, the program counter value should be increased. And then we learned that the size of the RISC-V instruction is 32-bit, it's the 4 byte. So the program counter value is increased by 4, PC plus 4, or some control instructions such as branch instruction or jump instruction, we need to fetch some instruction which is located on some different target PC. So sometimes the instructions are fetched from the target address or target program counter. So these are some basic operation to support the operation of the RISC-V instruction. So computer hardware, computer processor need to support these types of instructions. Okay. So based on what we covered in the previous slide, these are some hardware to support the operations. These base operations of the instructions. So what is required? So first we need instruction memory. So these instructions are stored in the instruction memory, and then the instruction memory has some what port are has address port and then instruction port. So this for this instruction memory, if the address values are input to this instruction memory, the instructions are generated from instructions are read from the instruction memory. So, and then also we need to calculate the program counter value, PC value, and then okay, and then let's go to the register file. Also, for the arithmetic, most of the instructions require operand from the register files. So, and then also some arithmetic instructions requires to write the result data to the register file. So, what are required? And this is the register file. Registers, some group of registers, and group of registers are called the register file. So, and we sometimes use the abbreviated form RF. So this register file requires some register number, and the register are indexed by the register numbers. So we this REST file requires a 3 ports for the 2 ports for the read operation, like x1 and read for the read operand, and then the third register index, third register number is required for the write operation, like a destination register RD, the RS1 and the RS2. So in order to store the data, the register files need the data input port, and you need the width of this data input. Also, the register file require the data output port, and then there are two source register numbers in the register file. So that means that the register files need has two data output ports, like for the RS1 and then RS2. And then, as I mentioned, the computer hardware requires the ALU to generate the result of the arithmetic and the logical operations. And then the data memory is also required. So for the data memory, the address is the input of the data memory, and then so the data memory support the two different types of memory operation, like load and store. Load double word and store double word. So that means that for the load instruction, the load instruction generate the address from the ALU, and if this address is input to the data memory, the data is read from this data memory. So data memory needs the data output port, the DOut. Also, for supporting store instructions, the data memory requires data input port, because what is the operation of the store instruction? The SD reads data from the register file, and then SD stores this data to the data memory. So data memory requires the data input port. And then the program counter value should be increased by 4 for the normal case, and then by the target address for the branch instructions. So in order to calculate the next program count value, we need the update logic, like PC plus 4, and then this is the target PC of the branch instruction. So these are the hardware components to support the operation I mentioned in the previous slide. So we start from this baseline. But in the computer, in the real hardware, what does this mean? So that means that two inputs are merged, and then one output is generated. Actually, in this real digital logic, this operation is not possible. That is very similar to the short of the electric wire. When the two electric wires short, then what happened? Disaster. So actually, in the real implementation of the digital hardware, this is not possible. So what is this case? So there are two drivers. So what is driver? The values are generated from some digital logic. Then this is called the driver. There are two drivers here, and then one output is generated, and this is not impossible in the real digital hardware. So how can we implement this part? Okay, here and here. We need to use the multiplexers. So this is the multiplexer, so MUX here. And then if you took the digital logic design course, the multiplexer is composed of 2 input and 1 output and selection signal. So the selection signal should be also generated from the some other unit, and then this unit is called the control unit, and then this selection signal of the mux is called the control signals. So based on this hardware component of the computer processor, we need control logic to generate the control signals, and then this control signals is required for mux hardware. Also, these registers and then data memory. Actually, some instructions such as the add instruction needs to write the data to store the result to the register file, but other instruction like store double word, this store instruction does not store the data to the register file. So this register write also should be controlled. So sometimes some instruction needs the register write, and then some other instruction does not require register write operation. So this register write should be also controlled. So this is the also register write is the control signal. Also, this is the ALU, and then ALU support the different types of arithmetic and logical instructions. So that means that we need to also distinguish the operation of the ALU. So ALU requires also control signals, and then the data memory also support the load and then store instruction, and then also the operation of the data memory is different for the different types of instructions, like memory write and memory read. So these control signals are also required. So I mean that this control unit need to generate these different type of control signals. So these are some baseline or some start point of the computer hardware. So we start from the operation of the instructions, and then based on this operation of the instructions, we list some required components of the computer hardware, required components such as the instruction memory, register file, ALU, and data memory. And then also we define some required port for each hardware component. And then we connect each hardware component, and then we insert the mux for some barrel control. Also, we define some control of each hardware, control signals for each hardware. So control units are also included. So this is some basic flow to design the computer hardware and then computer processor. So you need to remember this step. So from the operation of the hard software or some operation of the instruction, then we list some computer required hardware component, and then also we include some additional control signals. But this is the baseline. And then computer processor is much more complicated or much more complex to support the different types of instruction. So let's start from some basic of logic design, and then also this is some basic, and then this is I believe if you took the logic design course, that is the logic design course, then you are very familiar with this logic design conventions. But I quickly leave some some basic of the digital hardware or digital logic. So what is the digital logic? Digital logic only handles the two types of signal, two different signals like 0 and 1. And what does that mean? 0 and 1 mean 0 and 1 mean of the 0 and 1 of the digital signal mean the actually this is the high voltage and this is the low voltage. And then based on this voltage value, the computer digital hardware distinguish the value of the each component, each digital hardware. So this high voltage is this high voltage value is close to the VDD, so it's a supply voltage, not the exact the supply voltage, but it's very close to the supply voltage. And then no, sorry. I will start again. Forget what I explained in this slide. A digital logic just handles the two different values, 0 and 1, and then 0 is the low voltage, not high voltage, it's a low voltage, and then 1 means high voltage. And then this low voltage is similar to the close to ground voltage, and the high voltage is close to the supply voltage, VDD. And the digital hardware just handles these two different types of value, two different values, and two different voltage level. And then so low voltage is 0, and then high voltage is 1. And then one wire just handles the 1 bit. So that means that if the so we know that the instruction of the RISC-V, one instruction of the instruction 5 is composed of 32 bits. So that means that this, in order to implement these instructions, we require 32 wires. So 1 wire per bit. So multi-bit data encoded on the multi-wire buses. So this is it's just basic, true, just basic of the digital design, digital hardware design. And then there are two types of digital logic, digital hardware, combinational logic and then sequential logic. I believe you are very familiar with this combinational and then sequential logic, and I will explain explain later. So actually, combinational logic is just some simple logic or simple hardware. So and then this output of the combinational logic is determined by the input, and then after some delay, like delta delay, some other delay time, the output is generated, and then this output is the function of the input. I1, I2. This is the combinational logic. And then what does sequential logic mean? Sequential logic means that the data here can be stored at some defined event. This is the sequential logic. So these are the example of the combination logic, and then I think you are very familiar with this is combination logic like AND gate, adder, and multiplexer, and arithmetic unit. So what is defined? Output is defined, and then inputs are defined for the combinational logic. Then outputs are the function of inputs. That means that when the input values change it, and then the output value also changes. And these are the feature of the combinational logic. And then there's a sequential element. The feature of the sequential element is to store data at some defined event. this is the some definition of the sequential logic. So what is the representative sequential logic of in digital hardware? D flip-flop. So D flip-flop. And then what's the operation of the D flip-flop? The Q output of the D flip-flop is updated or sampled at the edge of clock. So this is the operation of the D flip-flop. So D flip-flop is composed of D flip-flop has two input ports D and clock, and then one output port Q. So that means that the Q output Q is updated or sampled at the edge of the clock. So this is the definition of the D flip-flop, and then so feature this is also a feature of the D flip-flop. So the flip-flop can store the data. So because the output is only updated at the edge of the clock. Also, we can add some control logic or control port to the flip-flop, like enable signal. So what does that mean? So when the enable signal is 1, the Q is updated by D at the edge of clock. But if enable is 0, then Q just maintain its original value. So we can just check the input signals for the sequential logic at the edge of the clock here and here and here, and then this flip-flop has the control signal and the write enable signal here. If the write enable is 1 at the edge of the clock, then the Q is updated by the D input D. But if enable signal is 0, then Q is not updated. 1 at the edge of the clock, if the control signal is 1, then output is updated. And so the clocking methodology, that's also basic of the digital logic design. So this is the basic combination of the combinational logic and sequential logic of the digital logic design. What does that mean? So digital logic is composed of state element like a D flip-flop, and then combinational logic. And then this combinational logic is the output of the combinational logic is connected to the input of the other state element. So 2. So this state element 1 and 2 are updated by the edge of the clock, like here, and then this is the combinational logic. So what does that mean? This input of this combinational logic is updated only at the edge of this clock signal by this state element. So after some delay, like a delay, the output of this combination logic is generated, and then this generated result is only updated at the next rising edge of the clock by the state element. So output of the state element is updated only at the edge of the clock. So that means that the delay of the combination logic should be smaller than the clock period t. So this delay, the longest delay of the combinational logic determines the clock period of the processor. Digital logic. And this is very important because normally the clock period or clock rate determines the performance of digital logic or computer processor. So for the hardware engineer, and then some hardware engineer try to decrease this delay of the combinational logic. It's just so important. The longest because the longest delay determines the clock period, and clock period is proportional to the performance of computer hardware. Then building data paths. So data path means the element that process data and addresses in the computer processor. So these are called some element or some hardware component. And this is the data processing or some operation of the data store and then data read. So these are the data paths of the computer processor, the registers, ALU, and MUXes, and memories. So these data paths just receive the input signals and then generate output signals. So these are called the data paths. And then as I explained, the data path is also determined by the operation of the instructions. And then after data path is defined, we added the control signals because some data operation of the data path should be determined by the control signals. And then so we first define the data path and then we will include the control signals later. So just start from the instruction fetch. So in order to execute the instruction, so we need to fetch the instruction from the instruction memory. So actually I already explained this. So for instruction fetch, we need the program counter, and then this program counter should be stored in the program PC register. It's a register. It's called the register, and this register is different from the register files. It's just some flip-flop. Because in order to fetch the data, some instructions from the memory, the address should be maintained until the instruction is output from the instruction memory. This is all same for the other instructions. So for instruction fetch, we need which data path is required. We need instruction memory, then program counter register, and adder. Adder is required for calculate the program counter value for next memory is the PC plus 4. And then what is the size of this register? Program counter is a 64-bit because we are handling the 64-bit computer system. So the address of the instruction is the 64-bit. So this is the width of this read address is also this is 64-bit. And then what is the size of instruction? What is the size of this port? Output port? It's the 32-bit because the size of the RISC-V instruction is 32-bit. So these are the data paths for instruction fetch. And then also we already defined the register file, and these register files and ALUs are required for all type instructions. So all type instruction requires the 2 source registers and then 1 destination register. And then between this source and the destination register, the all type instruction requires some operation, arithmetic or logical operation. So we require register files which has the 2 read port and then 1 write port. And then this register file receive the 1 write data and then generate 2 read data. And then all type instruction also require the ALU. So it is because this is some review of the RISC-V R format instruction. So this is a 32-bit instruction format. And then this OP code and function field determines the instruction type. And then this instruction has the 2 source register numbers and then 1 destination register numbers. So that's these are the sources. So based on this definition, we need this hardware. Now how about the load and store instruction? It's a memory type instruction. So we need the data memory, and then what's the format of the load and store instruction? And then load and store instruction requires immediate value. And then, because, for example, for the load instruction, is the load destination and some immediate value, and then base address. So address of this load and store instruction is just the immediate value plus x2 base address. So in order to support the load and store instruction, we need to first calculate the address of this instruction, and in order to calculate the address of this instruction, we need to calculate the immediate value plus base address. And then this immediate value, size of the immediate value is the 12 2's complement numbers, so 12 bits. So in order to generate this immediate value, so we need the immediate generation unit. So this immediate generation unit convert the 12-bit 2's complement number to the 64-bit number, integer number. Then this is the operation of the load and store instruction. So here, but as you can see, this is the 32-bit. So it's just for the generalization. So actually, this 32-bit comes from the size of the instruction, because there are some actually based for the different type of instructions, the location of the immediate field is different. So we just set the size of the input value of this immediate generation unit as the 32-bit. This is the size equal to the size of the instructions. So because it's the immediate field, this is the kind as a load instruction, but store instruction is also different. Store is different. The immediate field is different. So this is the immediate generation unit. So okay. So I will stop here. I think I need to explain about the branch instruction and other part in the next class. So I will stop here. So this is some basic of the process implementation, and then this is some starting point. So, and then I said that I emphasized that this chapter is very important in this course. So focus on this chapter, and then keep studying hard for this chapter, and then keep studying hard, keep working hard, and then also stay healthy, and then stay safe in the COVID pandemic. 예. 또 챕터 4는 여기서 끝내고요. If you have any questions, post your question on the blackboard or 피아짜. 네, 수고 많으셨습니다.